Well, welcome everybody. I want to welcome everybody to the Northwest Auto Care Alliance Lunch and Learn today, sponsored by Diagnation. I'm Gary Smith, and I'm here with the world's most unbelievable waveform wingnut that's ever graced the planet, Mr. Adam Robertson. And today, we're bringing this session to you from several diagnation cases, and lunch and learn is an important thing. We're going to kind of throw it back and forth between us, but Adam's going to run the presentation. We have some really neat case studies for you today. And we want to thank you for being here. Just remember that Diagnation is, in fact, your one-stop shop for support and diagnostic training and equipment when you need it. With that, Adam Robertson, waveform wingnut, over to you.
You know what? I'm going to jump right into the presentation because, Gary, you know darn good and well we have so much material that, frankly, an hour just doesn't do it justice. You know what I mean? So I'm going to pop in and we'll get started here. And you know, I have a question for you guys, and I think this is a really good question. You know, when it comes to lab scope waveforms, I've put up here known good versus presumed bad. Can everybody see this okay? Can I get a thumbs up? Gary, Brenda, okay, awesome, we're good to go, cool. At any rate, my question is this: is it good enough to have a known good waveform and a presumed bad, or maybe the one you take off the vehicle that you presume is bad? Is the ability to compare one waveform to another waveform really enough to properly diagnose a car? I mean, there's no question. There's no question that comparing known good to my waveform is a powerful tool. But where is the cutoff point? Where is the diagnostic efficiency in just seeing something that's different and really understanding? And Gary, you know this well. How do we make the decision of that noise that I see, that small difference that I see? Is that enough to be my problem or not? Or I guess to take this another way, is there a way that we could look at a waveform with maybe not having the comparison between known good and actually get diagnostic strategies out of that? And of course, Gary, you know exactly where we're headed with that. But before we go any further, Gary, I really wanted to share this with you. This was one of our Diagnation cases that I handled just this last week. And well, as Greg said in the chat room, this is the type of thing that makes me foam at the mouth. But this is actually, it wasn't even planned to be in this lunch and learn with you guys, but this is such a wicked cool case study. I had to share it with you. So obviously at the top of the screen, you'll see that I've got a Subaru 2.5. The firing order, you know, it's a Subaru, a little bit odd. It's a 1324, but I have an ignition sync on one. Now, let's make this a little bit bigger so you can see what really happened here. Guys, this is a shop. This is a shop that just purchased their first complete Pico lab scope kit. They got the pressure transducer, they got all the goodies, and these guys had barely even learned how to turn the scope on. And I get this call, and Darren, the gentleman who was working on it, he goes, Adam, he goes, you know, I got this 2.5 liter Subaru in the shop. And he goes, I'm convinced personally that it's got a bad head gasket. I'm convinced it does. It's a Subaru, of course, right? But he says, but it passes all of my conventional tests. He goes, Adam, he goes, it goes through a little bit of coolant every couple of weeks. I put my blue chemical on the radiator. I do a block test. It passes all that. But in my heart, I know it's got a head gasket issue. Is there something that we might be able to do with our Pico and our lab scope capabilities to maybe take another look at this? And I said, well, Darren, actually, there is. Why don't you use 3 channels? Now you're looking at these 3 channels on the screen right now. Why don't you use 3 channels? And so in blue, this guy right here, I had him do a relative cranking compression test with a current probe around the battery cable. Basically just looking the amount of current required to come up to the top dead center of the compression stroke on each cylinder as a comparative test to see if any one cylinder had more or less compression than anyone else. And then I said, and I want to take another channel right here in red, and I'd like to synchronize that to a spark event. And as I just mentioned, that spark event is the number 1 cylinder. All right. And then the best part of the whole thing, the goofy thing in green. I said, I want you to take that pressure transducer. I want you to take that Pico WPS 500X pressure transducer that has an incredibly tight tolerance at very low pressures. And I want you to adapt that to the radiator. Kind of like this, guys. Now, obviously, this wasn't the picture off this car, but if you look at that pressure transducer in this picture and you follow this hose, you can see that, come on, as creepy as it looks, this was easy. We literally took our cooling system pressure pump that everyone uses to look for coolant leaks. We ripped the hose off it. We stuck a hose on it. So instead of having a pump to pump up the cooling system, I can electronically read the pressure signatures in the radiator. So back to the picture. I think every one of you can look at this and say, wait a minute, that's kind of neat. Oh, it's really neat. Check this out. So we start cranking. And as we begin cranking, we get our rushing current. We begin here. There's my number one sink. Number one comes around, but you immediately see the pressure in the cooling system not just rise. That's what's so cool. It's not just rising in a minimal amount of pressure. There is a very vivid high pressure pulse here, 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 here. And if you look, it's in the same representation placed to the number one sink every 720 degrees of crank revolution. And as it goes high peak, high peak, high peak, high peak, the overall pressure in the radiator begins to climb and climb and climb. Now you got to keep this in perspective. Over here on the side, my range, guys, from this point here to this is only 1/10 of 1 PSI. As it slowly begins to climb, the very top of this screen is only 1 total pound per square inch, 1 measly PSI. Yet as it built from basically nothing all the way up to that 1 PSI over this 10 seconds of cranking, guys, 10 whole seconds here, I could pick out that very vivid pump that's happening just before the number one sink, following in firing order. That makes it cylinder number 2. So every time cylinder number 2 is coming up towards its ignition event or top dead center of the compression stroke, it's producing a pulse in the cooling system. And Gary, I'm telling you, if I could design a waveform, I don't think I could really build one as pretty as this, describing that number 2 head gasket leak into the cooling
Right.
system.
And here's the important thing about this kind of diagnostic, Adam. If you consider how long this client was messing around with the radiator bulb and well, maybe it is and maybe it isn't, and we're losing a little bit at a time, and it's not like a massive head gasket leak, but we're not sure. Look at what this diagnostic produced in 10 minutes. In 10 minutes, it was not only confirmed it had a head gasket, but it was confirmed which cylinder was leaking into the cooling system that fast.
And you know what really blew me away, Gary? And one of the reasons I enjoy instructing so much, and Gary, I'm sure you fall into the same category. We love helping guys during the day with their problems, is I get the opportunity to learn more too. It's a learning curve both directions. And when I showed this to Darren, I was so excited about him. Look at this. And he goes, yeah, Adam, he goes, that's so cool. So you know what I'm going to do? I'm going to take, and he really stopped me in my tracks. He goes, I'm going to take the pressure transducer off of, I'm going to go down the cylinder. I'm going to put my pressure transducer in there. But instead of the transducer, I'm going to put shop air in cylinder number 2 with the pressure transducer on the radiator to see if, when applying shop air to number 2, if I can see a rise in pressure in the radiator. And I got to admit, for as silly as that sounds, it's not something I thought of. I had to sit back and go, that's so freaking simple, but what
it's
a great
brilliant.
idea. It was brilliant. And sure enough, he called it. At any rate, I didn't want to crowd our whole day up that, but guys, I have to take this just one more small geeky step. I've now come to the point that this is a little bit too much work for me.
This is a foaming at the mouth part, by the way.
Yeah, I know. Greg called it straight out. This is where it happens. At any rate, I've gotten lazy enough, if that's the right term, that I don't even want to spill any coolant. Guys, I use one of these now. I don't know if you can see what this is. This is a blood pressure cuff. Now, literally a blood pressure cuff. I have 2 sizes. I have an infant size and a full size adult blood pressure cuff. And I've adapted my pressure transducer to the cuff. Get this, so I can wrap it around any available hose, upper radiator hose, lower radiator hose. I pump it up like I was doing a blood pressure test, and by golly, it will feel the pulses in that cooling system into the blood pressure cuff and show up on my lab scope screen too. Now tell me that your imagination isn't the only thing that holds you back with our diagnostics. Convince me of that. I just had to throw that in there.
Exactly.
So,
But you
I
know
know
what? That's really cool. What it does prove, though, is that we may have to start working on getting you a life. But please progress.
that, yeah, that's actually pretty
What a
true.
yeah, but what a great idea with a blood pressure cuff. You know, you're doing something here with that blood pressure cuff that is often talked about in other classes, which is when you use a scope and you use transducers, your diagnosis is limited only by your imagination. And obviously your imagination elevated a level there with that blood pressure cuff thing, because what a cool, quick idea for using that to get pressure. I mean, that's amazing.
It's just crazy, but it works great, Gary. It's just insane. At any rate, not to take up our whole program here, Gary, we had two different topics we wanted to get to today. And I have put a high-speed CAN-C waveform on the screen. And Gary, if you'd like to run with this, it'd be great.
All right, hold on. I'm answering a text or a chat.
Already? Wow. All right.
Yeah, they're asking how you're hooking up your blood pressure cuff to the transducer, and I said through the puffball squeezer.
Yeah, and actually, well, I mean, not see, here goes our whole day is shot now because of questions.
Yep, sure is.
But anyway, guys, you know, most of your blood pressure cuffs, especially the cheaper ones you buy like this, they have the gauge and everything on them, but you still need to have the pump to pump it up. So you pump it up and then you use the T fitting of the output that would normally go to the gauge like this. That's where you put your pressure sensor. And I found that if I pump this up, if I get it to sometimes, you know, 50, I mean, really get some pressure on that cuff, you can see those minuscule little pulses. It takes some practice, but heck, what else are we going to do? Right. So
exactly.
At any rate, let's talk about this, Gary, if that question's answered, because I'm totally stoked about this next topic.
All right, so this is really neat, guys, and we're only going to spend about 5 minutes on this or less, but this is so important to diagnostics. And since we're doing lunch and learn, we want to share with you guys a concept here with 2 slides on CAN bus waveforms, where we have a very distinct problem setting multiple CAN codes, okay? And one of the reasons we want to do this with you is we've got something to share with you. But the way I'd like to do this is everybody that's on right now and looking at this waveform, I want you to key your eyes in on the center of the waveform where you see 2 big dips in the blue and the red. Okay, focus on the blue and the red at the top where Adam's circling. 2 big dips. And also notice the ramps on the communication packets, okay, that are following that one in the middle. Now, what we want to do today is we want to be quiet for 30 seconds. We're going to do this rapid fire so we don't lose a lot of time in this session. But I want everybody to look at that waveform for 30 seconds. We have 30 seconds to answer this question and type into the chat what you believe is wrong with that. Go, 30 seconds.
And as you guys are typing this in, I'll throw just a couple other things your way. A standard high-speed CAN waveform should run a bias of about 2.5 volts. This is only running a bias of about 1.5. And the positive should go up, or the high should go up approximately a volt, while the low goes down about a volt. There are far more rules to high-speed CAN-C than that. But at the very basics of even what the bias is, this waveform is completely wrong. Sets, as Gary said, a multitude of communication codes up to and including the point that we could have a complete no start. But Gary, to make things worse as they're typing in there, when I took and built a math channel right down here in what you see as a dark purple, that math channel is the differential in pressure between high-speed CAN-C positive and negative. And this differential in pressure is what a true, honest, perfect high-speed CAN-C waveform to represent. So the
Right.
really frustrating part, Gary, and we're almost done giving their 30 seconds. The real frustrating part about this is that you do have quite a bit of communications happening. You can
That's right.
talk to modules, you can get codes, so you have communications, but just not enough to get the car to work. Gosh, Gary, I mean, where do you start on something like this?
Okay, well, here's the cool thing. We got a lot of really good answers. Okay, one of them is a driver failure and maybe a CAN node. One said, one is a really good thought, which says seems to me like a floating ground issue. And you're almost on to something there, Kenneth and Maggie, because I'll tell you right now, that's where we're playing. Okay, now that waveform that you were looking at before Adam flipped the slide, which is actually the one you're looking at now with a decoder on it. The problem is we have an unpowered module on the network that's dragging the bias down. Now, this waveform that's right here, and I love Greg. Greg's response was call Adam. That was what's wrong with the waveform? Call Adam.
Thanks,
so,
buddy.
But the really neat thing about what we're just covering here for a minute is that communication network problems are one of our most challenging areas of diagnostics right now. And what Adam and I have done is we've put together a really dynamic full 8-hour class on a 4-step process on how to visually look at these waveforms and understand the electrical characteristics that you're looking at on the screen, such as this. Because if you think about the power of the waveform we just showed you, and we can visualize in seconds of pulling that waveform up and know that that characteristic means that there is an unpowered node pulling that network down. Guys, we just cut out the first 3 or 4 hours of our diagnostic. So Adam's going to do a quick ditty on this slide, but I want to point something out to you before he rolls on with today's case study. And that is this. Adam and I have put together that class to give you guys the theory and the practical application and the ability to use that 4-step process to isolate a network node fault or wiring issue literally within minutes to an hour instead of an hour to 3 hours. So we're really excited about that. And we want you to watch out for the availability of that class on ASCCA at Bimmers. We're going to be doing it at ATE East, and we'll likely be doing it at Vision next year. This is a real game-changing diagnostic methodology for networks that Adam and I have put together for you. We're really excited to bring it. Adam, back to you.
Well, it's groundbreaking because all of my previous diagnostics on networks, I had my own kind of steps, but now, Gary, working together on so many of these, sometimes we get more than one comm problem a week, Gary, through diagnostic. We get a bunch of them. And
sometimes we get 3 a day.
It's crazy sometimes. And to be able to just look at a waveform and go, I have an unpowered node. That's all I did was get a waveform, and I'm telling you the type of problem we're chasing. That is wicked cool, guys. And the only reason I put the next screen is because when we looked at the differential and pressure, this is a situation where the ability to completely serial decode it and all this advanced stuff that we're learning in the field, it told you nothing on the failure of this because every single node, every single message was received, counted, and spoken about. Yet it's got a barrage of codes. It's wicked cool. And I'm going to throw one more before we jump on to our magnetic reluctance discussion. Gary, this is another one that we spoke about in pretty good detail. Completely different failure, completely different. But once again, one of our multiple, or I should say 4-step approaches to diagnostics. When I see this type of detail, I know where to go once again. Isn't it going to be crazy, Gary? And I don't want anyone to take this the wrong way, but isn't it going to be crazy when we show these guys that one of the steps most of us have been taught in every CAN class we've gone to is we get our ohm meter out and we measure. Gary, correct me if I'm wrong, man. We've done it for years, 2 decades for me. We get our
60
ohm meter
ohms
out and we check for termination resistance. And now I'm to the point that that's not one of my first steps because Gary, if there's a problem with termination resistance, we know what it does to the balance of that network, to the antenna of
Right.
that network, you know.
That's why this class is going to be so important, because it's going to simplify everything that you guys are doing out there in CAN diagnostics. Believe me when I tell you, this is really awesome stuff.
Well, how about enough of the teasing on that? Yeah, well, I guess if you guys, if you took anything out of those last couple slides, guys, you are going to have to find a way to get into our 8-hour communications class. It's going to blow your minds. It truly is. That's it. We'll get it out there for you. We'll let you know when it's coming. But anything else you want to throw in here, Gary, or do you want to?
Nope.
All
nope.
right.
Roll on, brother.
Now back to our normally scheduled program. So I'm going to come back to the same question that I just asked. And actually, right now, you guys might go, well, Adam, no, I don't think it's enough, because we just showed you in a couple slides on my question, do you think comparing known good to presumed bad or vice versa is enough for diagnostics? And the answer to you right now, after just seeing those few waveforms, should be no, Adam. I want to be able to look at that waveform without a comparison. I want to look at that CAN waveform, for example. I want to look at that and say, I have a module that has no key on power. I want to look at that CAN network and say, Adam, I think this car has a blown fuse. That's insane to come up with answers like that, but we can really teach you how to do that. So let's approach something that we did on this program back in February when we did part 1 of this for the first time, and we were asked to bring it back. Getting, I guess, a little bit more down to earth, I've got 2 different vehicles on the screen in front of you. I have a 2011 Ford Ranger 4-liter overhead cam in both pictures. One of these runs absolutely perfect, while one of them won't even start because it has no spark. Now, you need to think about this. One of them, absolutely perfect, no problem at all. The other one, absolutely no spark. Take that back. Every now and then when you turn the key on, it'll bang the spark and pop back through the intake or pop through the exhaust. But literally, one is a complete no start, the other one runs fine. Now, what I did is a wee bit of a challenge for you. I said, hey, I took a cam waveform in red right here. I took a crank waveform in green right here. Over here, I took a cam waveform and a crank waveform. If you truly look at both of these, and guys, you really need to consider something. We had the very unique advantage in this diagnostic. We had the very unique advantage to literally be able to park both cars next to each other. I literally had a running 2011 Ford Ranger here and my dead one here. I could compare every waveform on the car. We could swap any part we wanted. And boy, let me tell you, they swapped every part possible and it never fixed the vehicle. All right. So I'm not telling you which one is good or bad. Heck, I'm not even going to tell you that one of these is the problem. But what I can tell you is this. You need to understand more about how the waveform is produced. It's not enough. I guarantee you guys, it is not enough to just be able to look at the squiggly lines and the squiggly lines. I'm telling you that in my book, or I should say, heck, our book is not real diagnostics. All right. So before we can attack this, I think we need to start here. I think it's fair. And of course, I'm leading you down this path. I mean, you could say, well, Adam, there's a lot of things that could cause that not to spark. I know. We're going to talk about cam and crank waveforms, though. That's the point I wanted to get to. I think it's important before we go any further to realize that there are a few different types of rotation or position sensor. All right. Heck, we'll just call them cam and crank sensors for lack of a better term. And actually, I'm going to group them into basically 4 different types. 4 different types. We have the VR or MR, which guys stands for variable reluctance, magnetic inductance. All right. I hear them called by just about every word out there. It's obviously the simplest construction. They are usually just a passive device, which means They can produce voltage on their own. They don't require any extra help, all right? And actually, they rely on the changing of magnetic fields, which I'll show you how, which becomes important, to produce that pulse, all right? Then we move on to Hall effect designs, all right? Now, all I'm going to say about Hall effect at this point is they can detect static or not changing magnetic fields. Few different designs of them out there. Given time, or maybe another lunch and learn with you, I can go into those, but I don't see us having a lot of time for that today. I am going to make another point here, though. When you get into magnetoresistive style sensors, I put a note after this that said, hey, magnetoresistive style sensors, although very similar in what we think we see with our scopes and what we see with their operation, they can detect or read a truly stopped position. And it's one of the reasons that on a lot of our anti-lock brake and dynamic stability control systems today, our wheel speed sensors are magnetoresistive. And we can literally, if you've never had the opportunity, guys, it's awesome. You should try it. But I can literally take a wheel and stop it, have a waveform, move it a little, and the waveform changes. It picks that up. So we can critically measure wheel speeds down to true zero. All right. But
yes, hey, Adam, can I
yes,
add something to that?
yeah,
This
go
is
ahead.
really important with magnetoresistive in reading in the stop position. That's one of the main reasons why a lot of modern day cars, and even some older ones like even the early 2000s Chevrolets and GMs with the, 7X, 24X crank sensors kind of thing, those run encoded magnetoresistive. And the reason for that is for a fast start crankshaft sensor system to fast start, it has to know what the position is when the key is on and the engine is stopped. And it can do that with magnetoresistive within 6 degrees of crank rotation. So anyway, I just wanted to add that it's not even just all about ABS. Any kind of magnetoresistive is going to give us the ability to see what a stopped rotation position is before we start calculating.
Well, what's actually great about the comment you made there. Like I said, these are higher sensitivity. They can be encoded. But what's really cool about what you said, you brought it and applied it to quick start systems for cranking. And let's look at the challenges our manufacturers had. Look at the Series 2 3800 V6, for example, that GM had beginning in about 95 through almost 2000. Guys, we had some very serious problems with those kicking back, firing, and blowing the intake manifold off.
Yep.
Yeah, because they were starting out of time. And even Ford with they had that Duratec 3-liter, it did the same thing. And one of the reasons that they would explode, obviously, they're trying to start at time, is they were relying on that. Okay, we started seeing a signal. Woohoo! Let's go bang. Well, they could be 180 degrees out pretty easy.
And they were.
And so this really
it's funny because that's what we used to see in the GM shops. And whenever it would happen, somebody would yell Buick across the shop, right? It Buicked when it backfired and blew the intake off. So
yeah, for those of you who haven't seen it, it is violent when that happens, by the way. But
yeah.
At any rate, and the last one of these are obviously the optical designs, where we have, some type of slotted wheel where we're shining a light through and picking it up. But I did make a few comments. It's well beyond the scope of this class with you guys today. But optical designs, I put down, they're subject to failure. Guys, it didn't matter if you were working on Nissans or heck, aftermarket distributors like Unilights, or let's go to heck, the GM LT1, who even believes that a manufacturer like GM would stick an optical distributor that relies on clean slots, a high res and a low res, under the weep hole of a water pump. Are you kidding me? What did they think was going to happen to that? But at any rate, guys, optical designs did have the ability to provide the most precise edge detection. So as that wheel was microscopically turning, that edge was yes or no, which, Gary, and you'll agree with this, when relying on magnetic fields, there's, I guess, wiggle room is probably the right way to put that.
Right.
But
not too much, as you'll see in the next case.
That's right. Because of oil and coolants and other foulings, that's where we went. But if I were to take this to the next step, I would have to say, but aren't there also a few different designs of reluctor rings or tone wheels or coders, heck, whatever you want to call it, but the basic idea of that reluctor. I'm putting here, there are 3 basic flavors of this. All right. There are various designs with different tool counts. Some will have more than 1 row on them. Many cases, they'll include an offset or a missing tooth or missing teeth for synchronizations. Come on, guys. You have all seen it by this point. And I think it's a good idea to bring something up here. I make this mistake a lot when I'm teaching class and speaking. If you were to take a crankshaft reluctor ring, just a crankshaft, and let's say it has 2 missing teeth, pretty common. It's a 60 tooth minus 2, for example. A lot of times when I'm discussing that or even doing my diagnostics, I refer to that sink as number 1 sink. And I just want to make a point here that even on a crankshaft reluctor ring where there's truly a missing tooth or teeth for a sink, you don't truly know what that missing tooth represents as far as true piston position. And depending on the and depending on the manufacturer, that sink could be anticipation of number 1 coming, or heck, anticipation of number 8, you know. So
on a GDI, Adam, it's going to be exactly that. And on a diesel, it's going to be exactly that, which is predictive because they have to have start of injection time calculated.
And we have to get that figured out awfully quick. So predictability makes more sense than wait until we've seen enough in such a sense, you know. At any rate, guys, they come in a couple different designs. Once again, we have the solid designs. Solid designs are typically steel or cast. They're capable of manipulating the magnetic field. You know, they'll have teeth in them, whatever it be. You see a lot of those out there. One I want to warn you about, however, is the embedded magnetic encoder. We're seeing, Gary, we're seeing more of these, and I'm seeing a lot of problems with them. Jeep is a good example. Chrysler is a good example with that. But we are finding and have found embedded magnetic encoders in wheel bearings. Look, I can say I am actually one of those guys that installed a front wheel bearing, pressed it into the hub and everything, just to realize there was a magnetic encoder under the seal, Gary, under the seal. And I had it facing the wrong direction, so there's no ABS signal. It's like, dang, man. So
we get calls on that on Toyotas on the rears all the time.
You know, one of the things I sometimes ask the guys to do, I say, you know what, if you don't have the reactive piece of paper, or you're not comfortable because all your screwdrivers are magnetized now, if you don't have a way to feel where the magnetism is, a lot of times I'll ask guys, just put it in like a sandwich bag, zip it shut, and take some filings from, say, their brake lathe and just sprinkle it on it. It'll stick to the side where the magnetic encoder is. You know, it's a cheap trick, but, you know, it works. And then, of course, guys, we have the slotted plate for your optical designs. Now, remember when I just said we're starting to see some problems with magnetic encoders? Guys, take a look at this picture. If you haven't run into this yet, I took this picture off of a Dodge Journey. This is a camshaft, okay? This particular camshaft has not just a standard, you know, solid style reluctor ring. It has a magnetic encoder as the reluctor ring. So inside this piece of rubber here, if you want to look at it that way, you can see where the magnets live. I have magnet, 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 space, magnet, magnet, space, magnet, magnet. So it's encoded with embedded magnets instead of having visual slots. But take a look at this encoder. You're saying, but Adam, that encoder looks like it's picking up, well, metal. It's a magnet, guys. Now, a frustrating thing that we've run into is the metal that sticks to these magnets can alter the magnetic field and cause cam and crank synchronization codes or camshaft codes that are hard to figure out. But then you got to ask yourself another question. Well, Adam, if there's a bunch of metal stuck to my encoder, where did it come from? Well, if you work on 3.6s, I thought it fair to throw this your way too. A lot of problems, guys. Not picking on the Chrysler 3.6, but they have a lot of problems with their intake cams. They're wasting these things left and right. And obviously that metal has to go somewhere. And, you know, I'm gonna back up to this picture for a second too and throw something else your way. I mean, we could sit here and do case study after case study and blue car failure after blue car failure and all of that stuff. But I'm going to warn you, on vehicles like this 3.6 Chrysler that run a magnetic encoder, simply putting a magnetic parts tray on the valve cover to throw all your parts in can affect the magnetic field strength of the encoder. And I've seen a couple case studies now, been involved in a couple where we have magnetic field interpretation issues with them. So I just thought I'd throw that your way. Some of the Jeeps right now are running these magnetic encoders right on the back of the crankshaft underneath the flex plate. And we're having lots of delamination problems with the rubber that holds them together and just lots of creepy problems, but it's really behind where, really not where I was headed in this class. So we talked about there being a few different flavors of crankshaft position sensor. I want to focus right now on the VR or MR operation basics, because it's going to take us back to the case study, this 2011 no spark Ranger with the 4-liter overhead cam that I really want to apply this to. All right. So it's my opinion that if you're going to look at a waveform, you've got to have some understanding of what created it. If I said that a VR sensor was a passive sensor, it produces a voltage, it's like a mini alternator. However you have been introduced to a magnetic reluctance, typically 2-wire sensor, very, very commonly found in cranks and cams, wheel speeds, been around for a long time. In my opinion, it's critical, guys, that you understand how this actually creates the waveform and what caused the squiggly line to do what it did. So here's what I've done. And this is for a short, sweet introduction. This is written very well, in my opinion. All right. But I wrote it.
If you do say so yourself.
You know what? I'm going to say so myself because I think it's that good. But seriously, guys, think about this. The basic idea of a magnetic reluctance sensor at its most basic idea is we're going to take a permanent magnet and build a core. So I've got a core built right here of a permanent magnet. You can see I've got a south pole and north pole. Guys, it's just a permanent magnet, always has that magnetic field strength. All right. Then what we're going to do is we're going to wrap that with many, 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 many windings of copper. See, here's the idea. It really is a mini alternator. Think about this, guys. I mean, if you've got an alternator on a car and it's spinning around that big the rotor, you know, that's hooked to the belt, that rotor's spinning, it doesn't produce any voltage until that alternator's turned on. We have to turn that rotor into a magnet. But when we turn that rotor into a magnet, all that magnetic energy cuts into all these windings right here, those massive amount of translucently insulated wires. That magnetic field crosses those wires and a small voltage is introduced. But here's what you got to understand. A still magnetic field. So if this reluctor ring is not turning, this sensor is just sitting here, this magnetic field is not being moved. It's not being bent. It's not being twisted. So these copper windings all around that magnet aren't doing anything. But what we know is if we can bend that magnetic field, if we can make that magnetic field move and the magnetic field flux lines cross all of these copper windings, it will induce a voltage into my wires. But the trick really is this. You're saying, okay, Adam, so you're saying if the magnetic field isn't moving, if it's steady, it's no voltage. Absolutely right. Absolutely zero voltage produced if the magnetic field is in a steady state. But if I can get that magnetic field to bend, then my voltage is created. So here's what I'm going to do. And guys, this is super, super important to figuring out this Ford. Super important. All right. Like super, super. Here's the deal. I really, truly need to understand the 4 different voltage productions out of this little seemingly simple 2-wire sensor. 4 voltage productions. Here's what happens. Wouldn't you agree that this reluctor ring will be spinning around? All right. So let's say it's spinning in this clockwise direction. As it's spinning, I'm going to call this peak or this line the leading edge. As that leading edge is getting closer and closer and closer to this magnetic field, guys, that magnetic field is going to bend to meet that incoming piece of steel. Now think about this. So here comes this pulse. Okay, here's my sensor right here. Here comes the pulse. Here comes the pulse. When it gets close enough, that magnetic field is going to bend. It's going to be attracted. There we go. Okay, it's going to be attracted to that. When that magnetic field bends to be attracted to that post, as it bends to meet that bending across those windings produces a positive voltage. Pretty important, like real important. So it bent to meet the incoming pulse. But then, guys, if it bent to meet this leading edge, what happens when it's in direct alignment, like you see in this stopped animation? If it bent to meet it, and then it lines up directly, is this lineup causing a movement of the magnetic field? Think about this, guys. It produced a positive voltage to see it come in. When it's in direct alignment with it, the magnetic field isn't moving. So on our neutral peak, it's going to produce no volts, 0 volts. But then here's the cool part. If this was turning, then when this post leaves, when this peak leaves this area, that magnetic field is now going to do what, guys? It's going to bend the other direction to basically say bye-bye. I mean, it literally is just going to watch it leave. Well, when the magnetic field bends to watch it leave, it produces a negative voltage. And then our sensor is in direct alignment with a valley. When it's looking directly at the valley, no magnetic field movement, 0 volts. So let's see if I can make heads or tails out of this with a real waveform. Here is a known good crankshaft position sensor. Looks to me like a 60-tooth -2. At any rate, here's a crankshaft sensor. You know what? I'm going to make this bigger and make it easier. Watch. I'm going to start right here for lack of a better place to start. All right. As the peak is entering the magnetic field, he starts building positive voltage, right? He's reading the positive voltage, and then the voltage drops to 0. When? When does it drop to 0? If the magnetic field bent to see the post come in and it produced a positive voltage, then the next step is when it's directly lined up. When it's directly lined up, there is no voltage. But then we know that when it's directly lined up, it's going to be leaving, and then the magnetic field bent the other way to watch it leave. It produced a negative voltage. And then it went back to 0 when the peak was there. So we saw the post enter the magnetic field, positive, line up, 0, leave, negative, valley, 0, positive, 0, negative, 0, positive. So it goes through that rotation. But something really weird happens when we alter the number of teeth. Now, see, look back at this. I believe that if what I'm telling you is at least close enough true, it's how it works in my brain. If what I'm telling is close enough to true, then I believe that this post, every one of these are going to create a similar waveform. Similar. However, now we've got this huge vacancy to deal with. How much during this vacancy, how many volts should this sensor be producing while it's in a line with this vacancy? How much should it be producing? Because in this vacancy, it was 0. You should say, well, Adam, in this vacancy, it's going to be a longer 0. And that would actually be true. Wait a minute. So you're saying, that's exactly what I'm saying. We had positive 0, negative 0, positive 0, negative 0, positive 0, negative, big long 0, positive 0, negative. So this long 0 point was produced because our valley was wider than in these other sections. Gary, does that make sense to you? I mean,
Yeah,
I'm trying to make it as simple as I can. But why,
Absolutely.
why do we need to know that? I mean, what difference does that make? Look,
So let's say that's the number one signature, right? Or the predictive of number one. That becomes a really important chunk of the signal because everything inside of the DME is timing itself or synchronizing itself to that
and
with the rest of the engine.
okay.
So that's not just ignition, that's variable valve timing, that's all of it.
And isn't it true? This waveform is one of the few indicators the PCM has on where a particular piston is at any point in time. I mean, how important is actual piston position in an engine? A lot of times we don't think about it in that respect. But when we talk about things like ignition timing, for example, ignition timing is based off of where the piston was at when we decided to throw the spark. Let me ask you, Gary, how important is ignition timing in an engine?
Probably equally as important to mechanical valve timing because they all go hand in hand, or you have a drivability, right?
Or pistons in the pan, one or the
Or
other.
a no start.
There
right?
you go. Bingo.
Or an intake that Buicks right off the top of the engine.
Hopefully not while you're standing in front of it too. Haircut. Yep. Hey, so I did want to throw one small part in here, guys. For those of you who do happen to be playing with a Pico, or guys, this is even better. I don't care what lab scope you have. I don't care if you're running an ATS, a Snap-on, a little one-channel U-scope. I don't care what you're using. This is an incredible resource, free to everybody. Did you catch that part? Free. That's already good.
Download it free.
Oh, free, man. Go to the Pico website, picoauto.com, download Pico Scope 7. And even without having the Pico box, when you open that software, this page called guided tests is going to pop up. If you take nothing else out of this program, nothing else, you owe it to yourself to put this on your computer at home or at work, wherever you want to. Open it up, go into guided tests, and play around in these options. By the way, see this button that says don't panic? You owe it to yourself. Read that. It's going to blow your mind, and all for free. But the rest of it, things like charging and starting and sensors and actuators, ignition, all of these are exactly what you think they are. They give you this type of information. And Gary, how valuable is a piece of information like this?
Yeah, it's fabulous.
I mean,
and well, any really good scope is going to give you that. For example, in our diagnostic TP scope, we have that whole setup, as well as ATS actually does that, and Pico does it. So and I think, and I could be wrong, I don't play with Snap-on a lot unless I'm forced to, but I believe there's even a database in there that's similar that you can use for hookup. But it is a great resource no matter how you slice it.
Absolutely. And like I said, it really doesn't matter what scope you're using. Some of these resources can be incredible. So don't forget that it exists. All right. So let's go back to our 2011 Ford Ranger. I feel I have to give you more of the story because there's, in our business, Gary, there's always more to the story. And that more to the story is super important. But long and short of this 2011 Ford Ranger came in. It was a Radley timing chain. Guys, this one has the chains in the front, the chain in the back. It is a huge job and a questionable job, by the way, with Adam's advice, to perform on these 4 liters. They're very, very, very complicated engines and have a high failure rate. The point is, Radley chains on this engine, if you're going to do a timing chain job on it, requires the pulling of the engine and putting all back together, put it in. They brought it in running and driving. They replaced all the timing chains, guides, tensioners, you name it, put it back in. It never ran again. They assumed, which I got to admit, not a bad assumption, that more than likely we now have a synchronization problem between the camshaft and the crankshaft. I mean, heck, we had all the chains off. So what do? They tear it all back apart again, drop the engine, pull it apart, double check your marks, your dots, your lineups, your tools, whatever you want to use. And they believe that the synchronization is fine. So when I get involved, I get a cam sensor and a crank sensor. Here is the cam sensor. Here is the crank sensor. before I go any further, I'm going to make this fair to you and show you a known good one. Known good. Known good zoom. Our truck. Known good truck. Heck, let's get even creepier crazy with this. By the way, some of the advanced features of our modern scopes are wicked cool. Do you know what I've done in this picture? Well, actually, you can see it. But up here, I've got our truck. Here is my truck's crank sensor and cam sensor. On my second scope view below it, I've got a known good crank and cam. And sorry about the reversal of colors, guys. They just got plugged in backwards. I hope you could figure that out. But let's zoom in and take some detail out of this. I'm going to go back to here for a second. Let's take a look at the synchronization. Now, this is just a quick look, but I'm going to take my truck and I'm going to take that sync. And I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Approximately 10 peaks back is where my trailing edge of my cam sensor synced with this crank. If I look at my known good, 1, 2, 3, 4, 5, 6, 7, 8, 9. Guys, this cam and crank are in exactly the same spot as this cam and crank. My synchronization is absolutely perfect. But now let's get right to the crux of it. Some of you probably already saw this, but here's my question. Here's my question. I definitely see a difference comparing my known good to my truck. And in the interest of time, guys, because we are running up against the clock, I'm going to pick out the difference I see. Heck, I think all of you can see that here. I think you can see that, well, Adam, this one went peak coming in, peak lined up, okay? Peak going away, 0. I think you can see that as we described it. It almost looks to me, Gary, like there's an extra pulse here. I mean, It's got a sync. Look, guys, look at this. It has a sync. There's no doubt a sync there. A sync there, a sync there. There's no doubt the sync exists. However, there's this little, come on, boys. Let's see. That little bump from the 0 mark up is 1/4 of a volt, Gary. 1/4 of a volt.
And look what the other one's doing. Look at what the other one's doing. No quarters and no volts where it should be right there. Right.
But isn't it true, guys, that this extended 0 represents a wide gap with no pulses in it, right? It's supposed to be a 0. Then how could this one have a little bump there? How could it have a little bump when that's supposed to be a vacant 0?
Well, I'll tell you what, Greg got it. He just texted the answer.
Well, I'm glad he did. He better, you know what, Greg? You better get it because you're in every single class I teach. And if this one slipped by you, I would lose. Well, you know, at any rate, here's my point. I don't think, Gary, it's good enough just to see the difference. Me personally, I don't think it's good enough for me to go, wow, that one has that. This one has this. Cool, guys. Here's exactly why I don't think that's good enough. Because if you saw this like I did, I have to tell you why it's there. I can't tell you that, well, look at that. Huh? Let's throw a sensor. You think a sensor would fix this, Gary? Trust me.
No.
They've swapped a bunch of sensors out of it. There's no way a sensor is going to fix that. But this is why the understanding is so important. Because here is the actual reluctor ring on this truck. Peak, valley, peak, valley, peak, big 0, peak, valley, peak, valley, peak, valley. Now, hold on a second. Now I'm seeing, oh, it's starting to wake up out there. Now watch, I'm going to go back to this. Big 0, something in the way of my 0, Gary. There's something in the way of my 0. Is it a full pulse? No. It's not a full pulse, but something is in the way of my 0. Well, the way this is built, it has a pulse there, but they just cut it off. Wait a minute. What if this little thing, what if this little peak was in a little too far? Not all the way, but a little too far to where instead of getting a nice zero magnetic flux, no movement of the magnetic field, what if this was in just deep enough to flex that magnetic field just a wee bit? If it flexed the magnetic field just a wee bit, could it have produced a small pulse?
You bet.
And the answer is yes. And in order to prove that, when I was talking to the shop, I said, hey, loosen up the harmonic balancer, pull it out a little bit. And they pulled it out just a little bit, boom, fires right up. I'm like, your harmonic balancer's too deep. Because it turns out, guys, and this is the last I'll talk about this topic here. And no, I do not approve of this repair, okay? But I found the problem, then I'm done, okay? I can wash my hands of it. But here's the thing. When they put all new timing sets on this, it turns out the lower crank gear, it was an aftermarket Cloys, doesn't matter what it was just a little bit skinnier. Guys, a little skinnier, which meant the stock harmonic balancer went in just a little deeper. But just a little deeper was enough for that to get into the magnetic field, just the edge of the magnetic field, but it was enough. Now, of course, when I explained that to the shop, they go, well, Adam, let us show you what we did to fix it. Well, I probably would have wanted to put the right parts back on the vehicle because the depth difference of that gear might also change the straightness of it. But they said, hey, Adam, we went in and we ground off a little bit of that. Actually, we ground off a lot. We took 50 thousandths off of that, put it back in, truck runs great. But the whole point behind this, and I'll call it a day from my standpoint here, the whole point behind this was not just knowing that there's a difference in the waveform, but understanding what not only the difference is, being able to visualize the difference, but then more importantly, knowing what caused that, Gary. Because if you didn't know,
Sure.
and everyone, I'm just talking to you because, well, you're talking to me. The thing is, I think that just seeing that wouldn't be enough unless you knew that there had to be something intruding into that magnetic field. You'd have to understand circuit operation. Right. And this is just one small circuit operation, guys. Think about all the different circuits on the car that we deal with, from inputs to outputs to, heck, that new class that Gary and I are writing, which I'm going to throw my 2 cents on this. If you guys want to learn some wicked cool communication diagnostics that'll just blow your mind, you've got to attend our comm class. It's a game changer.
Because you know what, guys, with no joke, I mean, we all build classes. There's, it's been going on for years, instructors building classes. But I assure you of one thing, this class coming up on networks that we showed you the 2 waveforms on involves over 2 years of study and repeated application in real world cars. We didn't just come up with some idea to teach. In other words, this is the real deal when you go to see that class. But I want to throw one thing in on the end of Adam's case study here. There are 3 things that could be wrong with this. We know what was wrong with it. It was pushed in too far and it was catching that little edge, producing this green hump. Now that green hump was being read by the PCM as no space. In other words, they're expecting a long 0 space to identify number 1. Here they got no space. Now, I've had other case studies, 2 very interesting ones. One of them was a Hall effect where the camshaft got magnetized and it had a little piece of metal in the window that was creating the problem. And the other one was a Toyota 4Runner that had been apart like 22 times. And the first time it was taken apart, they dropped the crankshaft reluctor on the floor and smashed one of them down flat. And that was causing it. So there are 3 very distinct lessons that can be learned from this, whether it's Hall effect, magnetic, or magnetoresistive, which is understanding the theory behind that waveform that you have on the screen can make all the difference between whether you're really going to figure that car out or not.
You know what? And Gary, I waved some lucky chicken bones over your talking there and whammed one up on the screen for him, just like you were talking to Toyota. See that little broken tooth right there?
Yep.
That little broken, but that little broken tooth, here's where it's supposed to be. Here's a little extra broken tooth. understanding what causes the waveform gives you direction, man. And
Right.
here's something I've been apart many times, but ran horrible. And of course, I'm able to say, look, there's your 2 missing teeth that you should have. Here's 1 extra missing tooth. Ain't supposed to be missing. But you made it. I mean, we see these things. And the cool part is that we're able to pick them up on the waveform, not just by disassembling. Our efficiencies to do it this way are incredible compared to tear it apart and look for the broken tooth. Yeah. So at any rate,
That's
hey guys.
awesome. I mean, so what do you guys have any questions today? I know some of you may have seen this the first time we ran it or a portion of it, but what do you guys think about that session today in relation to understanding the true theory of how that waveform is being played on the screen? Do you guys see the value in that in diagnostics?
Oh, yeah.
Awesome.
You guys are able to talk if you want to unmic.
Absolutely.
I'm not
Let's
in a hurry
open up
for
the
anything.
floor and
Yeah.
have a discussion if you guys want to talk about anything or anything like that. Because we do have the waveform wingnut that is absolutely happy to dive in to any theoretical question that one might want to pop.
Well, as we're waiting for you guys to chime in, I just want to tell you, I appreciate you taking your lunch break or whatever to hang out with us. It's we had a really good showing today. I love seeing all these faces out there when we're putting on these
Absolutely.
classes. It's just awesome. And
Well,
you know,
you know
make
what
sure-
it does, Adam?
Yeah.
For me, I mean, we've both known and loved this group for a long time, and most, if not every one of the people on here today. What really impresses me about how many people we have on here at lunch today is what is that really showing us? It shows that it's worth every second that we come on to work with you guys, because you're here every time and you're just as dedicated as the instructors that are bringing you the information. And that, you know, look, when we can study together with a group like this, make ourselves better in our markets, help share information, learn and grow, what a great day, right? And, you know, I'm just very thankful to be involved with you guys for as many years as I have. And I know Adam is too. And I just want to thank you for your time during the middle of a really busy day to continue to expand your horizons and study diagnostics. So. All right. Well, I don't think we're hearing any questions. So with that said, what do you think, guys? Do you want to call it a day and get back on the floor? Our floor is remote. Your floor is concrete.
and our remote floor is freaking busy, dude.
Oh yeah.
But it's awesome.
Absolutely.
Yeah, absolutely. Yeah.
Awesome, guys. Well, thank you very much, Brenda and Carissa. Thank you very much for having us today and hosting this. And God bless you guys. We love you a lot out there. And feel free to get in touch with us if you need anything as usual.
Well, and it sounds to me like we'll all be able to meet up in person come September in Spokane, right?
Yep, that's going to be great.
We'll
And
continue her on.
that's where the CAN class is going on. That's going to be one of the first viewings of it. So get fired up for that one. That's an 8-hour event that's going to wear your brain out.
Mm-hmm.
Yes,
Well,
it will.
thank you both for hosting this for us and all the great information. And we appreciate everyone who also attended. Thank you.
Thank you.
Yeah, thank you.